Hello, class. Good morning. Sorry I'm a little bit late. Wow. Man, my computer is running super slow this morning. Okay, so I'm going to go ahead and get started because I have some stuff that I want to teach you guys today. Let me zoom in on the camera here. All right, and let me focus it. So I'm going to show you something that I think is kind of cool with logic gates. Okay. All right. So that's the first thing I'm going to show you today. So today is 7th. All right. So where is that? I've had a really long weekend with sick dogs. Whatever one dog had, she passed to the other dog, and now they're both sick. Okay, so let's suppose that I want to talk a little bit about the internal structure of the ALU, the arithmetic logic unit of a computer. And one of the things that a computer has to do is it has to add integers. Okay. So I want to show you how a computer might implement addition. All right. So let me tell you about, or let's just do an example of binary addition just to remind you guys. So let's say I wanted to add 1011 plus 101, something like that. Okay. Actually, I'm going to make this 111. Okay. So if I look at the ones place, I add these two together. Well, 1 plus 1 in binary is 2, which is that. Okay, base 2. All right. So I put 0 here, and then I have to carry the 1 over to the next column. So now I have 1 plus 1 plus 1, which is 3, and 3 in base 2 is 1, 1. All right. So I put the 1 down, and then I also have the 1 that I have to carry. So this is the first digit is called the sum digit, and then the other one, or the first bit, is called the sum bit, and the other bit is called the carry bit. So you have a sum bit and you have a carry bit. So 1 plus 0 plus 1 has a sum bit of 0, and it has a carry bit of 1. Okay? And then I have 1 plus 1 plus 0, which has a sum bit of 0 and a carry bit of 1. So that's my answer for when I add those two together. Okay? So let's just focus in on, for example, a single column of this. All right? You'll notice that we have a couple of things going on. We have the bits from the two numbers we're adding. Okay, so we'll just say in a single column. What do we have? We have a carry. We have a carry from the previous column. Okay. We have a, all right. We have the two bits that we're adding. Okay. And so these are the inputs. We get a carry from the previous problem, and we have the two bits that we're adding. Okay. So these are the inputs. Then what is output by this column? Well, we have the sum bit, and we have the carry bit for the next column. All right. So basically each column, it takes in a carry, it combines those with the two sum bits, and it produces its own sum bit, or that it combines it with the two things you're adding together. Okay. And then it produces the sum bit and then a carry for the next column. Okay. So a single column is called a full adder. All right. So what does a full adder do? Well, it's a block. So I'm going to show you the internal structure of a full adder in terms of logic gates in just a second. So you have a full adder, and it takes in two bits, A and B. All right. It has a carry in. All right. It produces a sum bit and also a carry out bit. Okay. So let's look at this particular. Actually, let's look at this particular. If we look at one of these columns, this column that I boxed in, you can see that A and B are both 1. So in this case, A and B are both 1. The carry in from the previous column was also 1. The sum bit is 1, so this one's not very interesting because everything is 1. And then the carry to the next column is also 1. Okay. So what does a full adder have to do? We can do a truth table. Okay. So let's do a truth table for a full adder. Okay. So we have our bits A and B, and then we have the carry in. And how many different combinations? Type it into the chat if you know how many different combinations there are for 3 bits. So how many different rows do I need in my truth table? Type it into the chat if you know. And then we have a sum bit that goes out, and we have a carry bit that goes out. All right. So I'm going to start listing the possibilities for the input. No one knows how many combinations there are? There's 8. Okay, so 0 plus 0 plus 0 equals 0. Okay. And there's obviously no carry. All right. 0 plus 0 plus 1, if you add those together, 0 plus 0 plus 1, plus 1 is equal to 0, 1. So that means that the sum bit is 1 and the carry bit is 0. Okay, same thing for this one. The sum bit is 1, the carry bit is 0. If we have 0 plus 1 plus 1, 0 plus 1 plus 1 is going to be equal to 1, 1. So that means we have a sum bit of 1 and a carry bit of 1. 1, 0, 0 is going to be that. So I'm just going to fill these in. Okay, so this is the truth table for a full adder. So these are the inputs and these are the outputs. So it is possible to make a full adder out of logic gates. So I will show you how to do that. All right. So let me show you what a full adder looks like. So you have your two inputs, A and B. Okay. And they go into an XOR gate. Okay. And then you have your carry in bit, which is XOR'd with A and B. Okay. Oops. And so you have basically a double XOR, an XOR of an XOR, and the output of that is going to be the sum bit. All right. So you can verify it for yourself if you want to. And then we have to do the carry bit. So the carry bit is going to be an OR of two ANDs. So this is an OR of two ANDs. One of the things that is ANDed is A and B. All right. So we have A and B, which is OR'd with, it turns out that it's this one ANDed with the carry bit. Okay. So if you do this, you can check the logic yourself. I'm not going to go over it because it's really tedious. But if you were to do that, you would find that this connection of logic gates produces the correct truth table for a full adder. Okay. Now, I haven't explained why this is, but basically each logic gate is 2 transistors. You need 2 transistors per logic gate. Actually, you might need more for XOR. So if we look at this, it's somewhere around 10 transistors are needed to make a full adder. Okay. So now, how do you make a circuit that can add together binary numbers? You make it out of full adders. So this is called sort of like modular design. Okay. So we're trying to build something that can add numbers together, and we make it out of this simple full adder block. So basically what we do is you take a bunch of full adders, okay? So let's say I wanted to add two 8-bit numbers. Actually, let's just show what it will look like for two 4-bit numbers. If you have two 4-bit numbers, what you would do, so let's say you have, these are the two numbers that you're trying to add, A0, A1, A2, A3, and you're trying to add that to B0, B1, B2, B3, okay? What you would do is in the first full adder, you put A0 and B0, and then the carry out gets fed into the next full adder, which also gets A1 and B1, okay? And by the way, the first full adder has basically a carry in of 0, so you'd feed 0 into that one. And then the carry out of this full adder goes into the next one. And then the output, and then the carry out of this one goes into the last full adder. And so if you add two, you may or may not have noticed this before, but if you add two numbers together, okay, like let's say you add two 4-digit numbers together, the most digits the result can have is 5 digits, okay? So you get all these sum bits out. So the sum, this would be sum 0, sum 1, sum 2, sum 3, and then when you add two digits together that have two 4-digit numbers together, or two 4-bit integers together, the result could have 5 bits depending on what the last carry is. Okay? So this is how one of the ways your computer might implement addition in hardware. So I think that's kind of cool to think about. So I wanted to show you guys that. If this kind of stuff interests you, then I would suggest that you look into something called digital logic design, okay? Because you can make some really cool stuff out of transistors, and it all has this sort of modular design. All right. So that's going to conclude our discussion of sort of computer architecture. So the next thing I'm supposed to teach you about is networks. Okay. Hang on a second. Okay. So we're talking about networks. All right. So networks are basically connected computers. All right. How are the computers connected? Let's talk about that. That's the first thing I want to talk about is how are computers connected? All right. How are computers connected? Well, there are 3 types of connections that IB wants you to know about. Okay. The first type of connection is what's called a hub. Okay. So if we have a hub, and let's say we have 5 computers, let's say C1, I'll say C0 because we're in computer science. C1, C2, C3, C4. Okay, they're all connected to this hub. Okay, the way a hub works is if C0 wants to communicate with another computer, it sends some data over either an Ethernet or Wi-Fi link to the hub, and then the hub just sends it to everything else. So everybody gets the message. All right. Even though this message is intended for one of the other computers in the network, the hub will send the message out to everyone, and 3 out of the 4 are just going to ignore the message. Okay. So the con of a hub is that it is inefficient. Okay. The pro of a hub is that it is simple. All right. There's not a lot of it's a simple way of making sure that of connecting computers together. Okay. Another type of way that computers can be connected is with a switch. Okay, and a switch is a little bit smarter than a hub, because a switch is going to know the identities of all the different computers. Okay. So let me see. I'm trying to draw this the same way. Okay. So let's say that the message is intended for C3. Okay. So this is supposed to go to C3. All right. Then what the switch is going to do, because part of this message is going to contain who is the message addressed to. And so the switch is going to read the message and say, oh, it's meant to go to C3. And so it's only going to send the message to C3. So it's discriminating who the message is sent to. Okay? So it's less simple, but it's more efficient. Okay? And then the third way that computers can be connected is with what's called a router. Okay? And a router, important thing about routers is that routers connect networks. Okay? Routers connect networks together. So, you might have a router, okay, and the router is connected to a switch, and the switch is connected to some different computers. Okay, and the router connects to the internet, which is just a big network. Okay, so this might be your house. Now, typically, the router and the switch come together. At least in the home, they come together. So, that Wi-Fi router that you have, it has both a router and a switch inside it. Okay, though you can purchase just one or just the other. All right. Do you guys? I'm curious. Do you guys rent your routers from the internet service provider, or have you purchased your own routers? I'm curious. Type it in the chat and share. So now let's talk about what is the physical connection, or what is the connection between the computer and the switch. What is it made out of? Looks like purchase your own. Yeah, nice. Yeah, I purchased my own router as well. So what is the form of this connection between the computer and the switch? Well, it could be an Ethernet cable. Oh, you know what? I forgot something when I was talking about routers. One of the important things about routers, because they connect networks together, is that they obey protocols. So a protocol is an agreed upon way that messages are going to be sent. Okay? So that's very important because, if router 1 is sending the message over the internet in a different way from router 2, then there's going to be confusion. So a protocol is an agreed upon method of communicating between computers. Okay, so it's really important that the router understands internet protocols, so it's sending the message in the right way. Okay, so there is one of the ways that you could have a connection between a computer and a switch is with an Ethernet cable. Okay. Now, an Ethernet cable obviously has the advantage that it is faster, or fastest, I should say. And I'm going to talk about why in a second. It has the disadvantage that it's has the disadvantage that it's a physical cable. So you're kind of, locked in place. You can't move around as much if you're connected via an Ethernet cable. Of course, the other one is Wi-Fi, which doesn't have the cable. It's slower. Okay? But you can move around. The reason I'm giving you pros and cons is because one of the things I've observed in the IB exam for computer science is they'll say, what is a pro of this and what is a con of this? So they'll ask you to do pros and cons of different things. So, I know it seems obvious, but I just wanted to give you some stuff to think about. So why is Wi-Fi slower? Well, because that might seem counterintuitive, because Wi-Fi is sending the signal as an electromagnetic wave, which travels at the speed of light. So it's like, why, if something is traveling at the speed of light from router to computer, why is that slower? The issue is that there is interference. Okay? So when you send a message over Wi-Fi, you're sending a string of ones and zeros. So maybe you meant to send 1101. So that's the message you're trying to send. But in the process of sending it, some of the bits get interfered with, and so the message that's received is not the same as the message that was sent. Maybe it was that. Maybe this is what was sent and this is what was received. Okay, so the protocol for Wi-Fi has redundancies built into it in order to make sure that the correct message was received. And that is the reason why it is slower. Okay, so the actual physical travel time of the message is less, but the message gets made bigger than it originally was. It becomes redundant in order to have a check and make sure that the correct message was received. Okay. So one of the things I wanted to talk about, and this is connected to your assignment for this week, is how can we know how can we know if a message has been distorted during transmission? This is very important. Oh, by the way, one of the things I wanted to say about Wi-Fi is that it's less secure. That's another con. Okay, so how do we know if a message has been distorted during transmission? So I'm going to give you a very simple way, and that's the topic of this week's assignment. It's called a parity check. It's not perfect, but it's a really easy way to wow! It's a really easy way to determine if a message has been distorted. Okay. So basically, what we do is, let's say we're sending an 8-bit message, 1 0 1 1 0 0 0 1. Okay. So this right here is the message. All right. So even though the message itself is 8 bits, I'm actually going to send a 9th bit, which is called the parity bit. Okay. And what the parity bit does is it is, all right, it looks at all the bits in the message, and if an even number of bits are 1, then the parity bit is 0. If an odd number of bits are 1 in the message are 1, then the parity bit is 1. Okay? So if we look at this, I can see that in this message there are 4 bits that are 1. That's an even number of bits that are 1. So my parity bit is going to be 0. Okay? So you send the message like that, with this parity bit included. Okay? Now what you do, so you send it, and let's say that during transmission, one of the bits got changed. So maybe the message becomes 1 0 0 1 0 0 0 1, and then the parity bit is right here. Okay, so if I look at this, so this is the sent message, this is the received message. Okay. Now what the computer that's receiving the message does is it looks and it checks for consistency between the parity bit and the rest of the message. Because what parity bit should the received message have? If I look at it, now I only have 3 bits that are 1. That's an odd number of bits that are 1 in the message. So the parity bit should be 1, but it's 0. Okay, so because there is inconsistency between the parity bit and the message, we know it has been distorted. Okay, so we could ask for the message to be sent again, something like that. Okay, all right, and this works even if the parity bit itself is distorted, because if the parity bit is distorted, then that would mean that, but the rest of the message is not distorted, then that would mean, again, lead to an inconsistency. So I want you to type it into the chat if you know, why is this not 100% accurate? What is a way that we could change the message that would result in the message being distorted, but the parity check doesn't catch it? Type it in the chat if you know. I'm going to wait. So yeah, it might get interfered to have different positions, but it's really difficult to change the order of the bits. That might happen if there is some kind of reflection of the signal, but I don't. But the most common thing is you have 2 bits distorted. Okay, very good. So yeah, if you have 2 bits distorted, then the number of bits that are 1 is still going to be even or still going to be odd. And so, but the thing is that the likelihood that 2 bits are changed is a lot less than the likelihood that 1 bit is changed. So you catch most of the errors, but you don't catch them all. So this is a simple, it's useful because it's simple. This is an example of a protocol you might use when you're communicating. You might say, we agree that all messages will include a parity bit at the end. All right. So your assignment for today is going to focus on the parity check. This week's assignment focuses on the parity check. So just keep that in mind. All right. I'm trying to think about what else I wanted to talk about. I wanted to talk about some different types of networks. Okay. There is a LAN versus a WAN. I don't know if it's called a WAN or a WAN. I don't know. But a LAN stands for a local area network. Okay. So it's called a local area network because it's a small geographical region. Okay. It's a small geographical region. Then you have a WAN, which stands for Wide Area Network. Okay, so a LAN might be a single building. Okay, whereas a wide area network might be an entire internet service provider or an entire state or something like that. Okay, so you have, yeah, so these are 2 different types of networks, and I wanted to talk about some sub areas of local area networks. So one of them is called a Wlan, which is a wireless LAN. So typically, when I was in high school, we used to have LAN parties where we would all bring our computers to someone's house and we would connect them up into a LAN. So typically a LAN is physical connections. And everyone would hook their computers up and we would all play Counter-Strike together. Okay? Good times, good memories from high school. LAN parties. And you'd always stay up really late and drink a lot of soda. Another type of local area network is called a Vlan, which stands for a virtual LAN. Okay, and so a virtual LAN is, so I'm going to talk about this one a little bit more. A virtual LAN is when you have a switch router combo or whatever, and you have C0, C1, C2 connected to it, and then maybe you have C3, C4, C5. Okay, and so you can see that these 6 computers are all physically connected to the same router. They're all part of the same network. But the router artificially breaks them up into 2 networks. Okay, so maybe you have LAN 1 and LAN 2. So you have 2 different networks. You have one network, one physical network, but the router is treating the different groups of computers as separate networks. Okay, so the router is not going to let computer 1 communicate with computer 4. All right, even though they're physically connected and could do so. So this is called a virtual LAN. Okay, so there you are having you have just one network, but the router is treating different groups of computers separately and making separate networks for them. So the example in the IB textbook I was mentioning that I downloaded online was different departments of a business. So you might have an accounting department and a sales department, and each of those might have their own VLAN network. So they're obviously all in the same building. They're all connected to the same routers, but you are artificially separating them because the accounting people have no idea what's going on with the sales team. So why would you give the accounting people access to the sales? All right. All right. So we're going to go more into this on Thursday. That's my lesson for today. I will see you in the Zoom room.